Hi, I'm Taronish, Geosoft's technical lead for geophysical modeling. In this web series, I'll cover the top 5 things you can do to improve your Earth modeling with VOXI. Each episode of this series will focus on a particular aspect of inversion, and will highlight best practices for auxiliary information, inverting large datasets, interpreting magnetization vector inversion results, building impactful constraints, and preparing gravity gradiometer data for inversion. So how did we come up with these best practices? Well, some of them were distilled from discussions with our customers. Geosoft's experienced team of geoscientists is always on hand to help support our customers with their inversion success. Sometimes we get questions on how to get the best possible result. After some brainstorming and testing, and some more testing, we come up with solutions to these questions. We've taken what we feel are the most common, most impactful things you can do to unlock the best inversion model and present them here in our top 5 inversion best practice web series. Before I begin talking about inversion best practices, I would be remiss if I didn't include a brief introduction to the inversion process. We'll start with a simple diagrammatic explanation before proceeding with a more mathematical explanation. On the left-hand side is a geophysical model space. There are many models that exist within this space, and 2 possible models are shown below. A model with basement topography, overlain with some cover rock, and another model with 2 separate bodies within a uniform background. On the right is our data space, and above is an example of some observed data. This is a gravity gradiometer survey observation that resulted from one of the possible models in the model space. The forward process is straightforward. You have a particular model in the model space that results in a particular observation in the data space. Inversion is the reverse process. We start with some observed data and we proceed backwards to find what model gave rise to the observation. In the real world, our observed data is not simply a point in the data space, it's a broader region due to errors in the observation. In addition, we see that in the model space, there are actually an entire class of models, really an infinity of them, that can explain the observations. This issue is called non-uniqueness. The way VOXI works is like this. We begin with some starting model, model 0, and calculate the forward response due to that model. We may find that the result, D0, doesn't agree with our observed data. So we calculate something about the difference between the observed data and the model result, and we perform a correction that takes us a little closer to a model that fits the observed data a little bit more. But we're not quite done yet, because you'll remember that we have an infinity of models within this smaller space. Back to our examples below, we may have some information that tells us we're not looking for a basement topography, but rather 2 distinct compact bodies. So we can impose constraints in the inversion that will preclude any models within this space that are similar to a basement topography.
The assumption of 2 distinct bodies is represented by a reference model that we've built,
and we would like to guide the inversion result towards this. We don't have to be entirely confident in the reference model. We can provide a rough idea and let the inversion proceed step by step to find a model within this smaller space that is as close to the reference model as possible and still produce a result that agrees with our observed data. This was a diagrammatic explanation of what the inversion process is all about. This slide has some of the common equations that govern the inversion process. At the very top is an extremely short equation that describes the forward problem we just saw in pictures. We have some Earth model M that is affected by some geophysical phenomena G that results in some observed data D. The inverse problem is also given by an extremely short equation, albeit one that masks the true complexity of the problem.
If we could find an inverse function, g inverse, and apply it to the Earth model M to retrieve the observed data D, then the solution would be as straightforward as the forward problem. However, g inverse does not exist, the corollary being non-uniqueness. Therefore, the inverse problem becomes one of optimizing the closeness of a predicted model and its forward calculated response to what we've observed and what we assume the model to look like.
We can quantify the closeness between the predicted model response and our observed data with this equation here, known as the data misfit. Here we have the observed data, and here the predicted model response. The difference between the two is normalized by the error in the observed data. When the difference is equal to the error, this data misfit equals 1. And we find that the inversion is fitting the data and not the error, which is good. We can also quantify how close the predicted model is to our preferred reference model with this equation here, known as the model norm. Here we have the reference model, and here the predicted model. The difference between the two is normalized by the error or the confidence we have in the reference model. When we are very confident in the reference model, we want the model norm to equal 0, which means the inversion is fitting the geology very well. In practice, we are seeking a model that satisfies the observed data and the known geology. So the inversion will seek to balance these two quantities before arriving at a final model. We can quantify this balancing act with this objective function here, where lambda is a regularization parameter that is adjusted by the inversion algorithm in successive steps. During each step calculation, the inversion tries to find a model that minimizes this objective function based on a condition that the data misfit is close to 1. When we plot the results of these step calculations, we'll get a plot like this, where each lambda represents an iteration in the inversion. The final model is one that minimizes the objective function with the condition we've specified. In this case, that the data misfit is close to 1. In VOXI, you'll see a progress report like this. This progress report gives you an indication of how the inversion is proceeding with the minimization of the objective function. The algorithm will proceed stepwise through a series of iterations, each with a different lambda and a different resulting data misfit. When the misfit is close to 1, the inversion has successfully minimized the objective function based on our criteria. VOXI's default is a data misfit of 1, but the user can adjust this if they'd like. In this brief introduction, I've covered some of the key concepts and equations requisite to any discussion of inversion best practices. First episode in this series, we'll discuss auxiliary information in inversion. You'll learn about choosing the best cell size, trend removal, error assignment, and optimum data sampling. Stay tuned for more.